In our first look at optimization, we talked about how to find critical points for scalar valued functions of multiple variables, which are, say, C2 on their domains. So what we will do in this video is 4 examples. For the first one, it will be routine. We will compute the gradient, and then we'll compute the Hessian. We'll find the eigenvalues, and that will allow us to reach conclusions. For examples 2 and 3, we will do the same kind of analysis. So we will compute gradients, find critical points, compute the Hessian matrix for each of examples 2 and 3. But at that point, we might need to do a little bit more work in order to figure out what kind of critical points we have. And then for the fourth example, what I would like to do is bring in Sylvester's criterion from linear algebra. This is essentially an alternative way to classify a quadratic form for a matrix without needing to compute the eigenvalues. For this final example, the function is a function of x, y, and z, which means that the Hessian matrix is 3 by 3. And in that particular case, I think Sylvester's criterion is preferable to computing the eigenvalues. For me, it's just a little bit faster. Our first example is f of x and y equals x squared plus 4xy plus 2y cubed plus 6. Let's just jump right into it. So we'll compute the gradient. Differentiating this with respect to x, we get 2x plus 4x. No, sorry, 4y. There we go. And then differentiate with respect to x, and we get 4x plus 6y squared. We need to figure out the critical points. That gives us a system of equations. For this first one, we want to figure out when x and y satisfy that 2x plus 4y equals 0, and likewise 4x plus 6y squared equals 0. Everything here is an even number, so when I write these down, I'm going to divide by 2. So in other words, when is it the case that x plus 2y equals 0, and also 2x plus 3y squared equals 0? Okay, let me subtract the first line times 2 from the second line. Okay, so this one times 2 is going to be 2x plus 4y equals 0. So I multiplied by the 2 I divided by earlier. Okay, there we go. 3y squared minus 4y equals 0 tells us that y is 0, or 3y minus 4 is 0, in which case y is 4/3. Okay, if y is 0, x is negative 2y, so x is also 0. Let me put that over here. Okay, so we have a critical point at the origin. No surprise if you look at the coordinates of the gradient. But also when y is 4/3, x is negative 2 times that, so x would be negative 8/3. All right, take a moment just to catch up before we move on to the Hessian. Now let's do the Hessian matrix. This is a C2 function, so it's going to be symmetric, but I want to think of it as taking the first coordinate of the gradient and differentiating it with respect to x and y down the first column. So that's 2 and 4. And then for the second coordinate, with respect to x and y down the second column, so that's 4. There's the symmetry as expected, and then 12y. All right. We want the Hessian at these 2 points. Let's start with the origin. So it's going to be 2, 4, 4, 0. If you want to, you can do the characteristic polynomial in order to find the eigenvalues. I'm going to use the trace determinant method. Maybe I'll do the characteristic polynomial for the second one just for some variety. The trace of this matrix is 2, and the determinant is negative 16. If your matrix has a negative determinant, it's a 2 by 2 matrix, that means that the product of the eigenvalues is negative, which means it must have been a positive times a negative eigenvalue. Couldn't be positive, positive, or negative, negative. Otherwise, the determinant would be positive. So as soon as I get to this point and I realize for my 2 by 2 matrix I have a negative determinant, I know it's a saddle. One of the eigenvalues is positive and one of them is negative. So that's why I like the trace determinant method. I think it's really fast sometimes for a 2 by 2 matrix. it doesn't immediately turn into a test for a 3 by 3 matrix. I just want to catch myself because I said I like it for 2 by 2 matrices, because you need 3 pieces of information for a 3 by 3 matrix. So for a 2 by 2 matrix, we have these 2 pieces of information, and that is enough to determine the eigenvalues. So this is really a great analysis for a 2 by 2 matrix. Okay, let me pause for just a moment. And if you haven't had a chance to do so, go ahead and analyze the second point. You can try this method if you'd like to. When I come back, I'm actually going to do the characteristic polynomial just for some variety. For the second critical point, although I don't think it's a good idea, we're going to find the characteristic polynomial. So what I'm actually going to do is take the determinant of the Hessian evaluated at that point, subtract lambda off the diagonal though, so we have the Hessian at -8/3, 4/3, minus lambda times the 2 by 2 identity matrix. And that's going to give us the determinant, sorry, keep forgetting to write that, the determinant of 2 minus lambda, 4, 4, and then 12 divided by 3 is 4 times 4, 16 minus lambda. I already know what the answer is with the trace determinant method, so we'll revisit that at the end. I don't get a commission every time you use it. I just think it's a much better way to find eigenvalues for a 2 by 2 matrix, or at least to find their signs. If you're just looking for the signs, it's like very fast. Okay, let's expand this out though. So we have lambda squared minus 18 lambda plus 32 minus 16, so plus 16, does not factor. The 2 eigenvalues will be given to us by the quadratic formula. So in the numerator, we'll have 18 plus or minus the square root of 18 squared is 324, I believe, minus 4 times 16. What I'm actually going to do is write 18 squared minus 4 times 16 so that I know I'm definitely right, but also have a point to make. Divide by 2. We are just trying to classify the quadratic form associated with our Hessian. We are not looking to actually find the eigenvalues. So, looking at this, the division by 2 does not affect the sign of the 2 eigenvalues. I can just work out what the signs are by looking at the numerator. 18 plus something is positive. So one of the eigenvalues is definitely positive. For the other one, I have 18 minus, but if you look at the square root, I started with 18 squared, and I subtracted off something smaller than 18 squared, so it's still real. It has to be if this one's real. But what we have is 18 squared minus a number, which is going to make this radicand here less than 18 squared. I'm going to take the square root, and it's going to be a number smaller than 18. All this to say is 18 minus something smaller than 18, so it's still positive. Okay, I don't know if I said that very well, but basically, if you just think about the terms inside of the square root, you can immediately see what the signs are. If you don't have a calculator handy, you can work out that it's positive and positive. So that means that we would think of the Hessian as corresponding to a positive definite quadratic form. So at our critical point, we go back to our function, we want to picture something which only allows us to go up. So it's a local min. Okay. We're done. In a moment, I'll put up a picture of this before we move on to the next example, but let me just return to the trace determinant method. The trace of our Hessian is the sum of the main diagonal. So 2 plus 16 is 18. It's also the sum of the 2 eigenvalues. And then the determinant of the original Hessian, so not the, like this alteration on it, just the original Hessian, is 32 minus 16 is 16. And that is the product of the 2 eigenvalues. And if you just want to know their signs, when you see a positive determinant for a 2 by 2 matrix, you think it was either positive, positive or negative, negative. And then when you look at their sum, it must have been positive, positive, because you can't add 2 negative numbers and get to 18. So just writing down this pair of numbers immediately tells me that I had 2 positive eigenvalues, and that's all I needed to know with this problem. And I just think it's just so much faster than all of this. So that's why I like the trace determinant method for 2 by 2 matrix. Okay, we're done with this example. I'll put up a picture and then we'll move on to our first example where we just have to think a little bit as we're doing our computation. Our next example is f of x and y equals x squared minus y to the 4th. You may see immediately what the conclusion is, but if you don't, you will by the end of this example. So there's something I'm looking at here that's going to help us classify this. Let's go through the motions though. So let's compute the gradient first. It's 2x and 4y cubed. Critical point is at the origin. It's the only one. But what is the 2 by 2 Hessian at the origin? It's going to be 2, 0, 0, 0, like that. All right, do not do the trace determinant method nor the characteristic polynomial here. When you have a diagonal matrix, or even just an upper triangular matrix, you just look right down the main diagonal. The eigenvalues for this matrix are 2 and 0. So it is positive semidefinite, which we discussed last time means that we need to do a little bit more if we're going to try to classify this because we don't want to go straight from this to a conclusion. Classifying this, though, isn't that bad. Just think about the axes. So what happens if, say, the number a is greater than 0, but y is 0? So imagine I'm on the x-axis in the domain. It would be a squared. A is just not 0 here. So that would be a positive output. On the other hand, if I go along the y-axis, what we would have is negative b to the fourth. For any non-zero b, that's going to be negative. So from the origin, there's a way to go up and a way to go down. This must be a saddle. So you might have seen that immediately just thinking about, how the axes would behave for this function, or how this function would behave along the axes rather. And that's the kind of balancing act that sometimes we engage in. So we'll look at a slightly more challenging example of a semi-definite classification before we wrap up with Sylvester's criterion. Our next example is f of x and y equals 2x squared minus x to the fourth minus y to the fourth. Take a moment to pause and compute the gradient, the Hessian, find the critical points, do as much as you can, and then I will come back and take you through the analysis of the critical points. With routine differentiation, your gradient should have looked like 4x minus 4x cubed and then minus 4y cubed, giving us 3 critical points, one at the origin and the other 2 at plus minus 1, 0. I put those together when I said that out loud because if you look at the even symmetry of this function, you realize that x and y only have even powers, which means the behavior of this function will be symmetric at 1, 0 and negative 1, 0. So that's maybe the first observation to make, is that if we classify one, we classify the other. So then we compute the Hessian matrix for these critical points. At the origin, we get 4, 0, 0, 0. So that is positive semi-definite, not conclusive yet. And then at the other two, again, the behavior will be the same. The Hessians are the same. We get negative 8, 0, 0, 0. So that's negative semi-definite. All right, so what we're going to do now is figure out what the behavior is at these 3 critical points by taking this right-hand side, our function, and rewriting it in a way that allows us to detect the behavior. So let's start at the origin. I think it's a little bit easier. We can say f of x and y. I'm just going to rewrite it. It's going to be x squared times 2 minus x squared minus y to the fourth. Okay. Let's do what we did a moment ago with example 2 and consider first going along an axis. So what happens if, maybe the easier one is to go along the y-axis, if x is 0 but y is non-zero? So I'll start by saying, what does f of 0 comma b look like? Well, this vanishes. We get negative b to the fourth. So we know that from the origin, there's a way to go down. Go along the y-axis in the domain and your function decreases. What about along the x-axis? So let y be 0 and analyze what's going on here. And it's also not too bad. It's a little bit more than going along the y-axis, but it's still pretty doable. What I'm actually going to do is an approximation. So I'll just write colon for that. We have here, actually, I'll write equals because I'll plug in a0 first. So we have a squared 2 minus a squared, and that's it. Okay. We want to classify the behavior around the origin, which means that a is approximately 0. It's not 0 if we're walking away from the origin, but it's very close. So a squared is going to be a non-zero positive number. It's going to be a very, very small positive number, but it will be positive. And then 2 minus a squared, if a is very close to 0, 2 minus a squared is very close to 2. It's certainly positive. So overall, this product will be positive. So I've written here that it is positive if a is approximately 0, not 0, but approximately 0, which means we have a way to go up. So we have a way to go down, we have a way to go up. Our origin is a saddle. I think that this is the easier of the two analyses we're about to do. So let me pause, give you a moment just to work through this. And then I will come back and show you how to do a very clever rewrite of this function so that we can classify these two. There are other approaches. So what I'm going to show you is not the only way to get to the classification for the other two critical points, but it's a way that I think is very elegant. For the other two critical points, we are also going to start by rewriting the function. So we'll say first, f of x and y is negative. I'm going to factor out the negative. And then what I'm going to do is take that quadratic term for x and the degree 4 term for x and use that to complete the square, where we're going to think of this degree 4 expression as like x squared squared. Okay. So completing the square, maybe I'll start by just factoring out. So x to the 4th minus 2x squared plus y to the 4th. There we go. Okay, complete the square. And we have x squared minus 1 squared. Now, if I expanded this out, I would have x to the 4th minus x squared, which is the minus 2 squared, or minus 2x squared. So we've completed the squared, but then we add a 1, which means I need to take off 1 in order to keep the equation true. Okay, so I took these two terms and completed the square here. Now what I'm going to do is bring this 1 in front. So I have negative, negative 1. This is actually 1. And then how about we just distribute the negative in general? Minus x squared minus 1 squared minus y to the 4th. I claim this is a wonderful way to write this function. Take a moment and see if you see why. The reason why this is so good is that 1 is f of plus minus 1, 0. Which means I can now compare the value the function actually takes at these two critical points to this other expression. If x is anything other than 1 or negative 1, this is negative. And if y is anything other than 0, this is negative. So if we are at any point other than 1, 0 or negative 1, 0, we are going to be subtracting off of the function's value at plus minus 1 and 0. Which means that if I'm at one of these two critical points and I move a little bit away from it, I'm subtracting off, so I know I have a local maximum. It's a strict local maximum, and actually, because this is really a global statement, that our function takes the value 1 at these two critical points, otherwise we subtract off of it. Not only do we know that we have local maxima, but we actually have absolute maxima. So we can say a little bit more. Where's my I lost a marker, but that's okay. These are strict absolute maxima. Both of them. Okay. Now, the truth of the matter is that I wrote this function to have this kind of nice form at the end. There are infinitely many ways to have a function, so you can't memorize every possible line of attack if you're looking at a semi-definite case. What I want you to see with this example and the previous one is the way of thinking about, like, well, what if I just thought about moving around near the critical points? Can I ascertain what the behavior of the function is? In both of these examples, I stayed with Cartesian coordinates. I didn't do any change of coordinates. I just kind of perturbed the x and y coordinates and thought about what effect that would have on the function. I don't think it would be a necessarily good example here, but you could also think about polar coordinates. Sometimes there are other coordinate transformations that can be useful. So the key is to kind of play around with the terms and see if you can figure out what the behavior is, even if the eigenvalues don't give it to you immediately. And sometimes it can be much harder than what we did. Okay, so I just wanted to give you a look at two examples of classifying Hessian matrices or classifying functions where the Hessian matrix corresponds to a semi-definite quadratic form. We will wrap up this video with one more example, which will be for a function of 3 variables. We're going to wrap up with this function. It's not a particularly exciting example, but I will use it to just quickly cover Sylvester's criterion with you. Just like before, go ahead and pause, find the gradient. There's only one critical point, so identify it, then go ahead and write down the Hessian. We don't need a trick to do the eigenvalues of the Hessian matrix, but since it's 3 by 3, I would rather have a slightly faster way than finding the eigenvalues. So if you'd like to, you could go ahead, find the gradient, find the critical points, write down the Hessian, and classify it if you would like to. I will come back in just a moment and make sure we got the same critical point. Then I will take you through Sylvester's criterion. Here's what I got for the gradient and Hessian. So for the gradient, just took a bunch of partial derivatives and it looked like this. Z is 1/2. Don't set up a system of equations here for x and y because both of these need to be 0. So if you thought about this in the xy plane, it's two planes which both pass through the origin. So their intersection is the origin. Our critical point is therefore 0, 0, 1/2. The Hessian is just a matrix of constants. So even if you didn't get this critical point, or if I'm wrong, we will still have the same analysis of the Hessian. So we have this 3 by 3 matrix. Because this function is not too hard, it's just a polynomial. The Hessian isn't too bad. I have a lot of zeros here. However, I would like to take a moment to look at Sylvester's criterion because if I can do something, really, if I can do anything other than compute eigenvalues, I'm usually happy. So let's take a look at that, and then we will return and apply it to this matrix. Okay, so here's Sylvester's criterion, and it's going to be a way for us to classify that 3 by 3 matrix without computing eigenvalues. So how it works is we want to compute a family of determinants. It's a sequence of determinants. And what we use are what are called corner minors, starting with the upper left entry and then growing diagonally down and to the right. So the first corner minor whose determinant we compute is just the top left entry, the A11. So it's a determinant of a 1 by 1 matrix. The next one we compute is the upper left 2 by 2. And then we compute the upper left 3 by 3, or I'll do like that. And we just keep going until we've gotten the whole matrix. So we will have in total determinants. Determinant is kind of an involved computation, but if I'm thinking about, oh no, look at all these determinants I have to compute, I would probably feel the same way about computing the eigenvalues. All right, so what is Sylvester's criterion? Compute all these determinants. The matrix is positive definite, so let's just call this matrix S. S is positive definite, if and only if this sequence of determinants that we're computing is, I'm going to try to stick with the order, green plus, there's a reason I'm doing this, plus, okay, plus, et cetera, et cetera. Okay, so I promise there's a reason for my colors, but if all of the corner minor determinants are positive, S is positive definite and vice versa. Okay. There's also a result for negative definite, and this is why the colors matter. S is negative definite if and only if the signs alternate in only one particular way. The first sign must be negative. Then you must switch to positive. Then you must go back to negative, et cetera, et cetera. Order matters. In order for S to be negative definite, it must be negative, positive, negative, positive, negative, positive, et cetera, until you get to the end. It is not equivalent to have positive, negative, positive. You cannot start with this as a positive entry. I'm going to give you not a proof of Sylvester's criterion, not even like a plausibility argument, just a way to understand, or not a way to understand even, just a way to have this committed to memory. So I'll give you like essentially the proof actually in the case that S is a diagonal matrix, because if you can remember this for a diagonal matrix, you can derive it on the spot, then you can just remember it. So I'm going to give you my mnemonic way of remembering the order. Okay. If you have signs that alternate, but in any order other than this, so maybe you have negative, positive, positive, or the order I mentioned a moment ago, positive, negative, positive, any other alteration of signs, it's indefinite. I won't write down anything more for Sylvester's criterion, but basically, if you have a 0 in there, it certainly could be semi-definite. I believe it can also be indefinite, but I actually forgot off the top of my head. These are if and only if statements, though. So if you get positive, 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 it must be positive definite. And if it is positive definite, you must have that. Similarly, S is negative definite if and only if you have these alternating signs in this order. Any other alternating signs must be indefinite. Treat an appearance of 0, a determinant of 0, as inconclusive. Let's say that. Okay, I'm going to give you a quick way to remember this ordering, and then we will return to our example and finish it. What I'm going to show you now is how I remember Sylvester's criterion. This is not a proof, it's like a mnemonic device for me. We know that all symmetric matrices have real eigenvalues and that they are all similar to a diagonal matrix. So let me see if I can classify this matrix instead. For a diagonal matrix, the eigenvalues are the diagonal entries. And also, anytime you have a diagonal matrix, the determinant is the product of the diagonal entries. So it's just much easier to analyze a diagonal matrix. Which means, imagine that all of my eigenvalues were positive. If I started computing corner minors, the first one would be positive. And then for the 2 by 2 upper left minor, it would be positive times positive, because again, it's just the product of the diagonal entries. And then positive, 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 et cetera, et cetera. So you can see that for this type of positive definite matrix, so this is an example of a positive definite matrix, one which is diagonal, all of the corner minors will give you positive determinants. Now here's where I have to stop and remember. So this is why I even have this explanation or this illustration really of how you can remember Sylvester's criterion. What if all of the eigenvalues were negative, which for a diagonal matrix is equivalent to having only negative numbers on the main diagonal? What are the corner minors in this case? Well, the first one is negative. But then when we take the product of the two numbers on the 2 by 2 corner minor, it's negative, negative, which is positive. So you see we flip from negative to positive, but then we have negative, 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 so that's negative again. And you see that the signs must alternate, and they can only alternate in one particular order. It must start negative, then positive, then negative again, then positive again, et cetera, et cetera. So I just wanted to show you this way of remembering. Now that we have seen Sylvester's criterion, we haven't proved it, but we've kind of visited it. Let's return back to our example and use it to classify this 3 by 3 matrix so that we can wrap up this video. Returning to where we left off, let's apply Sylvester's criterion to this matrix. Our first corner minor is this one. It's negative. Our second one is this one. I've dropped my colors, so everything will be orange. What is the determinant of this 2 by 2 matrix? It's negative 4 minus 9. Doesn't really matter what the number is. It's negative. Already we know it's not positive definite and it's not negative definite. And then if you because this is such a nice matrix, if you expand along the third row or the third column, you realize it's going to be negative 2 times this negative determinant. So the next one is positive. So it's indefinite. It has alternating signs, but it's not the same as the negative definite ordering. Any kind of mixture of signs like this, which is not negative, positive, negative, is indefinite. So we have a saddle. All right. I think that was faster than trying to analyze the eigenvalues of this 3 by 3 matrix. I hope you agree, and I hope that Sylvester's criterion gave you just a nice alternative way to classify quadratic forms. You could go back to the examples where we used even the trace determinant method and see if Sylvester's method is perhaps faster. Thank you for your attention.